What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In my last video I talked about properties of limits related to sums, differences, products, and quotients. That'll pop up in the top right here. In this video I'm going to focus on these two properties which are related to exponents and radicals. So let's jump right into it. First we have this condition that we have to check. Does the limit as x approach a of f of x exist? If it does, then we can apply this property. If it doesn't, we can't apply this property. We have to do different strategies or techniques, and I'm going to show an example like that in this video. So if it does, we can apply this property which tells us that the limit of this new function, which is the function raised to some power, equals the limit of the original function raised to that same power. So instead of having to think about what this new function looks like and find that limit, we can just think about the original limit and then raise that limit to the nth power. Let's try with some examples here. So first example, limit as x approaches -7 of this function cubed, which again, this is a new function where every single y value of the original function is cubed. But instead of thinking about that, we can hopefully apply this property as long as we check if this condition is met. Does the limit as x approaches -7 of this function exist? Let's check. -7 on the x-axis is over here. Yes, the function's continuous there. From the left, we approach 1. From the right, we approach 1, and f of -7 is also 1. So yes, the limit exists, it equals 1, and so we can apply this property which tells us that the limit of this function cubed is just the cube of the limit. So let me write this out as x approaches -7 of this function. So the cube of the limit, we found the limit was 1, and the cube of 1 is just 1. So we're good to go there. Let's try the next example. Again, we're starting with checking our condition. Does the limit as x approaches -2 of the original function exist? Here's -2. From the left we approach 6. From the right we approach 6. So yes, it exists. It equals 6. And so what we can say is that, again, this limit is the square of the limit as x approaches -2 of f of x. So it's the square of this, which we just found to be 6. So 6 squared is 36, and that's the limit. If you feel like you're getting the hang of this, pause the video, try these two examples on your own. Press play to check your work. All right, we're jumping into it the same way. We're checking our condition. As x approaches 3, does this limit exist? Here's 3. From the left, we get closer to 5. From the right, we get closer to 5. So the limit's 5. So I'm going to skip that intermediate step of writing out all the notation, and I'm just going to write 5 squared, which equals 25, because this is likely what you'll do once you get the hang of this. You'll just jump to that step. You'll say, oh, this is the same as the square of the limit. The limit's 5, so I'm going to jump to 5 squared, which is 25. Good to go. All right, this next one, the limit as x approaches 6. Does that exist? Yes, the function's continuous there. From the left, it's 2. From the right, it's 2. F of 6 is also 2. So yes, we're good to go. This is the same as the limit of f of x raised to the 4th power, which is 2 to the 4th power, which is 2, 4, 8, 16. Awesome. Hopefully that's what you got. You checked your work, and it's good to go. One more example here. This time our condition is not met. The limit as x approaches -4 of the original function does not exist. So again, all that means is that we cannot apply this property here. It doesn't necessarily mean that the limit does not exist. We can't just write DNE. We need to now think about what this function f of x squared looks like. And what this function looks like is it's this original function, but every single y value is squared, right? So we're going to have to the left of -4, if I approach from the left here, what this new function where every y value is squared is going to look like is, well, instead of being negative, it's going to go positive, right? When we square negative numbers, we get positives. So it's going to go positive, and from the left it's going to get closer and closer to what? What's this whole going to become? Well, it's going to be -2 squared up here at 4, positive 4. So this new function on this little section as we approach -4 from the left is going to look something like this. Now let's think about what happens from the right. Again, all these are squared, so we have 3 squared, that's like up here at 9, and then we're getting closer and closer to what? 2 squared, that's 4. So from the right, the limit is also 4. And I just think this is the coolest thing. We have a function where the limit as x approaches a number doesn't exist, but we square the function, and now the limit as x approaches that same number does exist, and in this case equals 4. And it's so cool that this happens in this example. And here's why it happens, is because when we square or when we raise to any even power, we could potentially have two different numbers that we raise to an even power and their results are the same, like -2 and +2. Those are different numbers, but when we square them, we get the same thing, 4. And that can happen with even powers. So when we see this stuff, we do need to check. We need to think about what the function looks like, because that's a thing that can happen. Kind of a cool thing. Hopefully that makes sense. Let's jump into talking about the next property here, which is very, very similar, but instead of dealing with exponents, we're dealing with radicals. We have the same condition we have to check. And what it tells us is that instead of thinking about this new function, which is a function to some nth root, we can think about the original function, find that limit, and then take the nth root of that limit. So it makes our life a lot easier. Let's jump into a couple of examples here. All right, first couple of examples, we have this same graph. I'm going to find the limit as x approaches -5 of the cube root of this function. So again, if you want to think conceptually, what this function looks like is every single y value is cube rooted, okay? But if our condition works, we don't even have to think about that. Does the limit as x approaches -5 of f of x exist? Whereas -5, it's over here. It's continuous there. From the left, it's -1. From the right, it's -1. So that limit does exist. It equals -1. And this is going to be some notation here we're going to write, which is that the cube root of the limit of x as x approaches -5 of this function, right? So we're now applying our property. Since the limit exists, we can say this is equal to this. So we can take the cube root of the limit, which we found to be, what was it again? -1. And so the cube root of -1 is just -1, right? What do I cube to get -1? That's -1. Awesome. Hopefully that's making sense. Let's try the next example. We're again checking our condition. The limit as x approaches 1, checking 1 here. Ooh, function's continuous at that point. The limit is 9. So now what I can say is that the limit of this new function, the square root of f of x, is the same as the square root of the limit. So the square root of the limit, sorry for my handwriting, as x approaches 1 of this function, which we found to be 9, and the square root of 9 is just 3. Awesome. Hopefully those examples are making sense. It's very similar to the last property, just slightly different. Let's check an example for this property where our condition is not met. All right, so same example here. Limit as x approaches -4 does not exist, but that doesn't necessarily mean that the limit doesn't exist. It just means we need to check and see what's going on here. So this function, every single y value is square rooted. So what's happening from the right is that the function is going to approach the square root of 2. And what's happening to the left, it's going to approach the square root of -2, which is a complex number, right? So the left limit and the right limit of this new function, where every y value is square rooted, is different. The left limit isn't even a real number, right? From the left, we're approaching the square root of -2. And from the right, it's the square root of +2. These are not the same. These are different. That's all we need to conclude to say that this limit does not exist. And in fact, I couldn't find an example. I couldn't find an example where the limit doesn't exist, you take the square root, and all of a sudden it does. So what's the difference between, square root or third root, whatever it is, and like squaring and raising to the 4th and to the 6th? And well, it's that we can't take two different numbers, square root them, and end up with the same number. We can when we raise stuff to an even power, like 2, 4, 6, 8, etc. In that case, we could take two different numbers, namely the ones that are opposites, like we saw with 2 and -2, and we can raise them to some even power and get all of a sudden numbers that are the same. We can't do that with a square root, right? Square root operation, as an operation, is 1 to 1. You can think of it. So I'm pretty confident that when we see these roots, if the original limit doesn't exist, then we can just say the final limit doesn't exist. But if you want to prove me wrong in the comments, please, I invite you to do that. I did try to find a fun example where that works, and I'm pretty convinced that it doesn't. So we're going to write DNE here, although we did take the time to think about what this new function would look like and justified it. And that's going to be it for this video. In the next video, I'm going to talk about composite functions and this property of finding limits of composite functions. But hopefully you enjoyed this video. Hopefully you helped. If it did, like the video, subscribe, leave a comment, do all that stuff. But most importantly, keep flexing those brain muscles, and I'll see y'all later.